This presentation is delivered by the Stanford Center for Professional Development.
So with that said, any questions about strings? We're going to do a bunch more stuff today with strings and characters, but if there's any questions before we actually dive into things, let me know now. And if you could use the microphones, that would be great. One more time, take those microphones out, hold them close to your heart, near and dear. They're lots of fun. They're your friend. Keep the microphone with you.
Actually, sorry, about the midterm, what's the cutoff for the midterm in terms of like class days?
Right, so the midterm for stuff you need to know, the cutoff will be Wednesday's class. So basically you'll have a whole week of material that you won't need to be responsible for that will be from this Wednesday up until the midterm. The other thing to also keep in mind is a few people have asked, well, do I need to know the book versus your lectures for the midterm? You need to know the lectures, and you need to know all the material from the book that is covered with respect to the lectures, which is most of the material from the book. But there's a few cases where, we go over something very quickly in class, or I say refer to this page of the book or whatever. That stuff you're responsible for knowing. Stuff that I've explicitly told you don't need to know, like polar coordinates, aren't going to be on the exam. Okay? So the exam will be more heavily geared towards stuff from lecture, but you still should know all the stuff from the book that we've kind of referred to in lecture as we've gone along. Alrighty? All right, so let's dive into our next great topic. Actually, it's a continuation of our last great topic, which is strings. And so if we think about strings a little bit, one of the things we might want to do with strings is we want to do some string processing that also involves some characters. So how are we going to do that? One thing we might want to do is let's just do a simple example to begin with, which is going through a string and counting the number of uppercase characters in the string. And the reason why I'm going to harp on strings a whole bunch, we talked about it last time, we're going to talk about it this time. Guess what your next assignment's going to be? It's going to be all about string processing, so it's good stuff to know. Okay? So we might want to have some function, count uppercase. And this is a function I've actually given to you in one of the handouts, so you don't need to worry about jotting down all my code real quickly, but you might want to pay close attention. And what this does is it gets past some string, str, and it's going to count how many uppercase characters are in that string. So it's going to return an int. And let's just say this is part of some other program, so we'll call this private, although you could make it public if it was, in some class that you wanted to make available for other people to use. So if we want to count the number of uppercase characters, what do we want to think about doing? What's the kind of standard idiom that we use for strings? Anyone remember? What? No? We want to have a for loop. I heard kind of for loop somewhere over here. Yeah, it's just raining candy on you. We want to have a for loop that goes through all the characters of the string, sort of counting through the characters. So we can do that by just saying for int I equals 0, I less than the length of the string, right? So str.length is the method we use to get the length of the string, and then I++. And this is going to loop through all the characters of the string. Okay, or actually it's going to loop through some number of times, which is the number of characters in the string. Now we want to pull out each one of the characters individually to check to see if it's an uppercase character. What method might we use to do that? Get a character out of a string at a particular position? Come on, I'm begging for it. Char at, yeah. I was like, where'd it go? It's just gone. Char at, and we'll just, for the delayed reaction, we'll do it in slow-mo. Anyone remember the $6 Million Man, that show? No. All right. Yet another thing, man, I'm just getting so old I got to hang it up. And the thing is, like, I'm not that much older than you. But it's just amazing what big a difference a few years makes. So char ch is going to be, from this string, we're going to pull out the char at position I. So now we've actually gotten we're going to loop through each character of the string, pulling out that character, and we want to check to see if the character is uppercase. We could actually have an if statement in here that checks to see if that ch is in between uppercase A and uppercase Z, which is kind of how you saw last time. We could do some math on characters. We're going to use the new funky way, which is to actually use one of the methods from the character class and just say if, and the way we use the methods from the character class, we specify the name of the class here as opposed to the name of an object, because the methods from the character class are what we refer to as static methods. There's no object associated with them. They're just methods that you call and pass in a character. Is uppercase, because this returns a Boolean, and we'll pass it ch to see if ch is an uppercase character. Okay? If it is an uppercase character, we want to somehow keep track of the number of uppercase characters we have. So how might we do that? Counter, right? So I'll have some int count equals 0 up here that I want to initialize. Who said that? It came from somewhere over here. Come on, raise your hand. Don't be shy. It's a candy extravaganza. So if character is uppercase, ch, then that count, we're just going to add 1 to. Okay? Otherwise, we're not going to increment the count because it's not an uppercase character. And then we end the for loop. So this is going to go through all the characters of the string. For every character, check to see if it's uppercase. If it is, increment our count. And at the end, what we want to do is basically return that count, which tells us how many uppercase characters were actually in the string. Okay? So any questions about this? This is kind of like an example of the sort of vanilla string processing you might do. You have some string, you go through all the characters of the string, you do some kind of thing per character of the string. In this case, we're not creating a new resulting string, we're just counting up some number of characters that might be in the string. Okay? So we can do something a little bit more funky. This is kind of fun, but it's sort of like, yeah, it's, you know, just basic kind of string and character stuff. Let's do something a little bit more funky, which is actually to do some string manipulation to break a string up into smaller pieces. And so what we want to do is replace some occurrence of a substring in a larger string with some other string. Sort of like your word processor where you do find, replace. You say, hey, find me some little string or some little word that's actually in my bigger document. I'm going to replace it with some other word. We're actually going to implement that as a little function. Okay? So what this is going to do, we'll call this replace. I'll call this replace occurrence just to keep the name short. But in fact, all we're going to do is replace the very first occurrence in a string. So we're going to get passed in some string, str. And what we want to do is basically have some original string, which is the thing that we want to replace, with some replacement string. So we're going to get past 3 parameters here. We'll call this repl for replace, okay? Which is the large string or piece of text that I want to replace some word in, the original word that I want to replace, and the thing that I want to replace it with. Okay? And so what I'm going to do, because strings are immutable, right? I can't change the string in place. I have to actually return a new string which has this original replaced by this string. So this puppy is going to return a string, and we'll just make this private again, although we could have made it public if we wanted to have it in a library that other people would use or a class that other people would use. Okay? So how might we think about the algorithm for replacing this original string with the replacement? What's the first thing we might want to think about that we want to do with the original string? A little concentration music. We want to find it, right? We want to see if this original string appears somewhere in that string, right? Because if it doesn't, we're done. Thanks for playing, right? But that's actually the good thanks for playing. It's sort of like you got no more work to do. And there's actually some methods from the string class that we can use to do that. So there's this thing in the string class called index of. And what index of does is I can pass it some string, like the original string I want to look up, and it will return to me a number. That number is the index of the position of the first character of this string if it appears in the larger string. So the larger string is the one that I'm sending the message to, and I'm asking it, do you have this original string somewhere inside you? If you do, return me the index of its first occurrence. And if you don't, it returns a -1. So I'm going to assign this thing to some variable I'll call index. And first of all, I want to check to see if I have any work to do. If index is not equal to -1, then I have some work to do. If it is equal to -1, that means, hey, you know what? You wanted to replace this original string inside string str. That original string doesn't exist, so I got no work to do. You just called like find and replace in your word processor, and the thing you wanted to find wasn't there. Okay? So in that case, all I would do is I would just return str, right? Sort of unchanged if I assume that I'm not doing what's inside the braces. If I do find that string, though, I'm going to get some index which is not -1, which is the position of this original string. So let's do a little example just to make this a little bit more clear what's going on. So if we were to call this function, and pass in the string str, so here's str that we're going to pass in. We'll just put it in a big box. And we'll say at this point in life, everyone's just friendly. So we say, Stanford loves cow. Right? Sometimes you have to distort reality in order to make an example. Right? So we have Stanford loves cow. That's our original string str. And we might want to say, well, you know, this is really not always the way life is. Really, the way life is we want to replace occurrence on str of the word loves with kind of a more realistic example like the word beads. Right? So what we want to do, and then this is going to be some string that comes back. We'll assign it back to str. And the question is, when we call this, what index are we actually going to find in here of the original string, right? So strings, we start counting from 0. So here's 0, 1, 2, 3, 4, 5, 6, 7, 8. The 9 is where the L is at. Okay, and it keeps going, 10, 11, 12, 13, just to put these all together, 15, 16, 17 is the L, and that would be the end of the string. Sorry, the numbers are a little bit small, but the key is that this L is at 9, okay? So when I call string index of original, it says, does the word or the string loves appear somewhere in the larger string? Yeah, it does. It appears at index 9, so that's what you get, okay? So if I've just got an index 9, and what I want to do is construct some new string that essentially is going to have this portion removed from it, how do I want to do that? What I want to think about is the way I construct that string is from 3 pieces. The first piece is everything up to the word I want to replace. That's piece number 1. The second piece is the thing that I actually want to replace the string I'm replacing with, right? So this becomes piece number 2. And then everything else after the piece I've replaced is piece number 3. So if I concatenate those 3 pieces together, I'm going to essentially get the new string which has this part replaced. And the question is, how do I find the appropriate indexes inside my larger string to be able to actually do the replacement? Okay? So first thing I'm going to do here is say, get me the first portion. So what I want is essentially the substring of the original string up to this L position. Okay? So the way I can do that is I can say str.substring, and I'm going to get the substring starting at 0 because I want to start at the beginning of the string, and I want to go all the way up but not including the L. That means the last position in substring, remember in substring you give it 2 indexes. You give it the starting point and the position up to but not including that last character. That's position 9. Where am I getting position 9 from this thing? From index, right? Index says, where does love start? It starts at position 9. I'm like, hey, that's fantastic. So 0 up to index, or 0 up to 9 is Stanford in the space. It does not include the L. So I get that portion. Then I say, well, to that, I'm not done yet, so premature semicolon there. Always got to watch out for that. Bad times. So what we're going to add to that is we're going to add the string that we want to replace in here, beats, which happens to be the string called the replacement, or RPL. And then to that, we want to add one more string, and that's essentially everything from after loves over to get that third piece. Okay? So what I want to know is what's the index of the position at which I need to get characters over to the end. That happens to be position 14. Okay? What is 14 equal to relative to the kinds of things I have over here? It's index, right? Because I have to first get over to the 9. Then I need to jump over the length of this thing, which is the length of my original string. So if I add to index plus my original dot length, what that gives me is the index from which I want to take a substring over to the end of the string. So if I want to take a substring, this becomes an index to the substring function, or the substring method. And so from the string, what I do is I say take the substring starting at position 14. Notice I haven't given a second index here. In this case, I gave 2 indexes. I gave a start and an end position. Here I just gave 1 index, and what happens if I only give 1 index? It goes to the end. So that's part of the beauty, is a lot of times you just say, hey, from this position, go to the end. And so that's what I get when I put all these 3 things together. And what I need to do is these 3 things are just pieces. I'm concatenating them together. I assign them back to str. Okay? And then when I return str here, I've gotten those 3 pieces concatenated together. So any questions about that? If love appears more than once, index of just returns the index of the very first occurrence. There's actually a version of index of that takes 2 parameters. One is the thing you're looking for, and the second is from which position you should start looking for it at. And so you could actually say, look for love starting at position 13, and then it wouldn't actually find loves in the remainder of the string. So there's a different version of index of, but index of always returns the index of the very first occurrence of the string you're looking for in that string. Okay? So let's actually do a little example of this in a running program. And we'll do replace occurrence. And one thing that actually goes on at Stanford which was I thought was an interesting thing when I got here as a freshman, is we don't like to speak in full terms, right? So if we want to Stanfordize some string, we do all these string replacements. We sort of say, you know what, if you have Florence Moore in your string, that's really Flo-Mo. And Memorial Church is Mem-Chu. Computer science, CS. Psychology, Psych. Economics, Econ. Your most fun class, CS 1068. Right, so it's just what Stanford's all about. And so if we go ahead and run this, right, here's the function we just wrote. Here's our little friend, replace first occurrence. Over here we called it replace occurrence. Here I'm being explicit saying it's only replacing the first occurrence. You could think of a way to generalize this to replace all occurrences in a string if you wanted to, but I didn't give you that version because I might give you that version on another problem set at some point, right? So what we're going to do is we're going to ask the user, enter a line to Stanfordize. Notice I want to put Stanfordize inside double quotes. So I've put it in these characters, /quote, which just means a single double quote character. That's how I print double quotes. So it says read line to Stanfordize, in quotes. I want to keep reading lines and Stanfordizing them until the user gives me an empty line. How do I do that? I check to see if the line the user gives me is equals to a quote. Okay, so if it's equal to a quote, it's equal to the empty string. That means, hey, you entered in, it's the user, we asked the user for a string, they just hit enter, they didn't enter any characters, that's the empty string, so we would break out the loop. It's our little loop and a half construct. Otherwise, we say, at Stanford, we say, and we Stanfordize the line. And when someone's finally done, we say, thank you for visiting Stanford. Ha ha ha. That'll be $45,000. All right. So, it's money well spent, trust me. Really. Okay, so replace occurrence is the thing we want to run. And we come along and it's running. Sometimes my computer's running a little bit slow. I noticed this weird thing last night. I'll just tell you a story while the computer is actually running. That I couldn't type ends on my keyboard for some reason. Then I restarted my computer and I could. So at this point, I don't know if I can type ends. Let's just hope we can. So I live in, I got the N. Florence, you should have seen it last night. I was like, N, I wasn't getting it. Florence Moore, major in economics, I can't even type today, and spend all my time on my most fun class. Okay, and so at Stanford we say I live in Flo-Mo, major in econ, and spend all my time on CS 1068. Okay, and now I hit return. Thank you for visiting Stanford. Go home. All right, so that's kind of a simple version of string replace or replace first occurrence. And notice you can actually replace multiple things in the same string as long as the string that you're doing the replacement on, you assign back to itself, and then we kind of do a bunch of these replacements in a row. Okay? So any questions about that? Are you feeling okay about string replacement? All right. So now it's time for something completely different. Although it's not completely different, it's just kind of different. And the idea is sometimes, I always say that, sometimes you want to do this. Yeah, because sometimes you want to do it, and other times you don't. Sometimes you feel like a nut. Sometimes you don't. Man, I got to start watching TV in this decade. All right, so tokenizers. What is a tokenizer? A tokenizer is something as a fancy computer science term. All this tokenizer is we have some string of text. What we want to do is break it up into tokens. That's called tokenization. And so you might say, Maron, what is a token? Like last time I remember what a token was, it's when like I gave $1 at the arcade and it got back like 10 tokens instead of quarters. And you're like, yeah, Maron, I never did that. I had an Xbox. All right, so tokenizers. Anyone ever go to an arcade? All right, just checking. All right, so a token basically is a piece of string, is a string that has on the two sides of it white space, right? So if I say, hello there, Mary, hello there and Mary are tokens. They are something that we refer to as delimited by white space, which means there is either spaces or tabs or returns or whatever in between the individual tokens. We like to think of tokens as words, but computer scientists say token. Token is a more general term because if I actually said hello there, comma, Mary, the there comma might actually be considered one token by itself because it's just delimited by space. Here's a space here and here's a space there, so the comma's in there. And you would say, but comma is not part of the word. Yeah, that's why we call them tokens and not words. Okay? So if we want to tokenize, there is a library that we can use in Java that actually has some fun stuff in it for tokenization, and that's Java util. So we would import java.util.star, and what we get for doing that is we get something called a string tokenizer, which is a class that we can use to tokenize text. All right, so we get this thing called a string tokenizer. How do I create one of these? Well, I'd say string tokenizer is the type, because that's the class that I have, and I'll call it tokenizer. Tokenizer equals, I want to create a new tokenizer. So I say new string tokenizer. And the question that comes up here is, well, what is the string you're going to tokenize? That is the string that we pass to the string tokenizer's constructor when we create a new one. So we might have some line here that we pass in, and that line is just some string that maybe we got from the user, for example, by doing a read line, and maybe we were unfriendly and didn't give the user a prompt. We just, like, the blinking cursor comes up and they're just like, oh, I got to turn it and write something. It's just like when you're writing a paper, right? The blinking cursor comes up and there's nothing there. You just got to fill it in. So you write some line, and then we can say, hey, string tokenizer, I'm going to create a new one of you, and the line I want you to tokenize is this line that I'm giving you to begin with. Okay? So once it gets that line, there's a couple things you can ask the string tokenizer. One of them is a method that returns a Boolean, which is called has more tokens. And the way this puppy works is you just ask the string tokenizer, like you would say tokenizer dot has more tokens, like do you have more tokens? Have you processed the whole string yet? So if you've just created the new line and this is the line, it's kind of sitting here like that. And if you say, hey, do you have any more tokens? It says, yeah, I got tokens, man. I got tokens up the wazoo. You want tokens? I'll give you tokens. And so has more tokens would return true. If you've processed the whole string, when you will see when we get there, it'll say, no, I don't have any more tokens. How do you get each token? Well, you ask for next token. And what next token does when you call the tokenizer with next token is it gives you the next token of the string that it's processing, okay, as a separate string. So if I started off the tokenizer with this line, I say, hey, do you have more tokens? It says, yeah. Well, give me the next token. So what it will return to you is hello. And it will be sort of sitting here waiting to give you the next token. You can ask, do you have more tokens? It says, yeah. Give me the next token. It will give you there and the comma. Because the default version of the tokenizer, the only thing that delimits tokens, delimit is the funky word for splits between tokens, are spaces or tabs or return characters. But for a single line, you won't have returns in there. And then you say, do you have more tokens? Yeah, give me the next token. It will give you Mary as a token that's sitting here. And then when you say, do you have more tokens? It says false. Okay? And at that point, you shouldn't call next token, right? You can if you want. You can experiment with it just if you want to experiment with random error messages. But there's no more tokens to give you, right? It's all out of love. It's so lost without you. It has no more tokens. Yeah, Air Supply. Not that I would recommend you actually listen to Air Supply, but sometimes you hear a song and you can't get it out of your head as much as you wish you could. Sometimes selective brain surgery would not be a bad thing, but that's not important right now. What is important right now is how do we put all this together to tokenize a line? So let me show you an example of the tokenizer. This one's very simple. All we're going to do here is we're going to ask the user, just scroll over a little bit. We're going to ask the user to enter some line to tokenize, and we're going to write out the tokens of the string R, and then we're going to call a method print tokens. What's print tokens going to do? It's going to take in the string you want to tokenize. It creates one of these new string tokenizers. I'm so lost without you. Scary. Just kind of see, can we make Maron snap? I know, it's a great song to listen to when you're like 14, you just broke up with your girlfriend for the first time. Yeah, and then after that you want to kill the next time you hear it. All right, so new string tokenizer. I'm glad we're having fun though. So what I'm going to do is I'm going to count through all the tokens. So I'm going to have a for loop, interestingly enough. Here's something funky. I'm going to have a for loop where the thing I'm going to do in my for loop, my test, is not to check to see if I've reached some maximum number, but my test is actually going to be to see if tokenizer has more tokens. So I have a for loop that's just like a regular for loop, but I start off with a count that's equal to 0, and you're like, that looks okay. I do a count plus plus over here, and you're like, that's okay. What are you counting up to, Maron? And I say, I'm counting up to however many tokens you have, and you go, oh, interesting. So my condition to leave or to continue on with the loop is tokenizer has more tokens. Okay? If it has more tokens, then I'm going to do something here to get the next token. I'm going to keep doing this loop. But what the counter is going to give me is a way to count through all my tokens. So I can write out token number count, and then a colon, and then write out the next token that the tokenizer gives me. Okay, so any questions about that? Let's actually run this puppy, make sure it's working. You feel free to keep singing now if you want, but be warned. All right, so we're going to do our friend What's our friend called? The tokenizer example. We're running the tokenizer. Inner line's tokenized, so I might say I, for one, love CS. We're very formal here. And it says the tokens of the string are, notice it got the I and the comma together as one token, because as we talked about, spaces are the delimiter. And so for, and then one with a comma, and then love and CS, and that's all the tokens we got. And so at this point you might be saying, yeah, Maron, that's great, but you know what? I really don't like punctuation. And sometimes I don't like punctuation, but I can't stop the user from using punctuation, because even though I don't like to be grammatically correct, they do. So how do I prevent them from being grammatically correct as well? Which is kind of a fun thing to do. What you can say is, hey, what I want to do is change my tokenizer so that it not only stops at spaces, but it's going to stop or consider a delimiter any of this list of characters that I give it. So you give it a list of characters as a string. So here I'm going to give it a comma and a space. Okay? And this version of the string tokenizer constructor, what it will do is it will actually tokenize the string, but think of the thing that you're using as your delimiter, or what chops up your individual tokens, as either a comma or a space or anything you want to put in that string there. Each of the individual characters in that string is treated as a potential delimiter. So if you say I, for one, love CS, no commas. Why? Because commas are considered delimiters. So it just gives you everything up to a comma or a space, and you could imagine you could put in period and exclamation point and all that other stuff if you just want to get out the non-punctuation characters. Okay? So tokenizing is something that's oftentimes useful if you get a bigger piece of text and you want to break it up into the individual words and then maybe do something on those individual words. Okay? Any questions about tokenization? Hopefully it's not too painful or scary. All right. So the next thing I want to do, today's to the smorgasbord of strings, is I want to teach you about something that's really gotten to be an important thing about computer science these last few years, which is basically this idea known as encryption. And encryption is something that's been around for thousands of years. All encryption is it's kind of like sending secret messages. You have some particular message, you want to send it to someone else, but you want to send a secret version of that message. And people have been doing this for thousands of years, actually, interestingly enough. They just didn't have very good methods of doing it until about the last, 50 years. But, they did it for a long time, and people broke encryption. As a matter of fact, there's this really interesting book by Simon Singh. I'll bring in a copy perhaps next class if you're really interested, about the whole history of encryption. It goes back thousands of years, and how wars and queenships and kingships and stuff were basically lost and won on the strength of how well someone could break a piece of code. But the basic idea of encryption, it probably dates back even farther than this, but one of the most well-known ones is something that's known as the Caesar cipher. Not to be confused with the salad, but the basic idea with the Caesar cipher, I picked up the wrong piece of paper. The Caesar cipher is that what we want to do is basically take our alphabet and rotate it by some number of letters to get a replacement. What does that mean? That's just a whole bunch of words. So let me show you a little slide that just makes that clear. Okay? So in Caesar's day, I will now play the role of Caesar. I considered wearing a toga to class today. I just thought that was fraught with way too much peril. So I just decided to bring my little Caesar crown. And I tried to find like a little crown of wreaths and stuff, but I couldn't. So I just got a little hat. And so the basic idea, say you were Caesar. I did crown myself, actually. I needed someone here to actually take the crown from their hands. And that was Napoleon. That's a whole different story. I just like to take history and mix it up. See if you're actually paying attention. All right. But so Caesar, the basic way the Caesar cipher works is we take our original alphabet. Here's all of our letters from A through Z. We take that whole alphabet and we shift it over some number of letters. Like let's say we shift it over 3 letters. So I take this whole thing, I shift it over 3 letters. So now the D lines up over here where the A should have been. So I've shifted over these bottom characters. And the characters that kind of went off the end here, like the A, B, and C, we're kind of like, whoa, we're going off the end. Where do we go? We just kind of shuttle them back around over here. Okay? So the basic idea is we're going to rotate our alphabet by n letters, and n is 3 in the example here, and n is called the key. So the key of the Caesar cipher is how many letters you're actually shifting. Okay? And then we wrap around at the end, and now once we've done this little wraparound, we take our original message that we want to encrypt. That's something that's referred to as the plain text. The plain text is your actual original message. And we want to encrypt that or change it to our cipher text, which is what the encrypted message is, by using this mapping. So every time an A appears in the original, we replace it by a D. And a B appears in the original, we replace it by an E. And a C appears in the original, we replace it by an F, etc. for the whole alphabet. Okay? So any questions about the Caesar cipher? This is actually an actual cipher that evidently historians tell us that Caesar used in the days of yore. And evidently, he was killed, so it didn't work that well. All right? But you can, most people, that's one of those things that when you were a little kid and you had like the super secret decoder ring, you're probably getting a Caesar cipher. Yeah? All right, any questions about the basics of the Caesar cipher? So what we're going to do is let's write a program that actually can be able to encrypt and decrypt text according to a Caesar cipher, and we'll do it doing top-down design. So we'll actually just do it on the computer together because it's more fun that way. And because I'm Caesar, I will drive. So we're going to have my Caesar cipher. All right, and I just gave you a little bit of a run method here as to kind of the very beginnings of the program. But all this does, it's not a big deal. It says this program uses a Caesar cipher for encryption. It's going to ask for the encryption key. That means it's asking for the number by which it's going to rotate the alphabet to create your Caesar key, or to create your Caesar cipher. And that's just our key. That's an integer. So our plain text, that's the original message that we want to encrypt. We ask the user for the plain text, so we just get a line from the user. And then what we're going to do is we're going to create our cipher text, or the encrypted text, by calling a function called encrypt Caesar. We're sort of giving a directive. It's kind of like the accusative case. Encrypt Caesar. And we give it the plain text, and we give it the number for the key that we want it to encrypt using. And then hopefully that will give us back the encrypted string, and we're just going to write that out. Okay? So how do we do this encryption? Right? So at this point, it should be clear that the thing we want to write is probably encrypt Caesar. Okay? So what we're going to do is we're going to write a private method. And what is this puppy going to return to us? String, right? Because that's what we're expecting, the encoded version of this particular message as a string. So we'll call this encrypt Caesar. And what's it getting past? It's getting past a string, which we'll just call str, and it's getting past some integer, which we'll refer to as the key. Okay? So if I want to think about doing the encryption, right, what I'm going to do is on a character-by-character basis, I want to do this replacement. I want to say for every character that I see in my original string, there's some shifted version of that character that I want to use in my encrypted string. Okay? So in order to do that, I'm going to use my standard kind of string building idiom, which says I start off with a string, which I'll call result, which starts off empty, right? It's just quote, quote, empty string. And I'm going to do a for loop through my string that I'm given to encrypt. So up to string's length, I'm just going to count through and get each character. So I'll do sort of the standard thing. I'm going to say ch, and I'm going to potentially get the character that I want to get from the string. So I'll say str dot car at chat at car at I. So I've now gotten that character. I want to figure out how to encrypt that character. Okay? So I could think to myself, wow, gee, well, encrypting the character involves all the stuff doing the shift and all that. That's kind of complicated. Maybe I should just create a function to do it. All right, that's the whole notion of top-down design. Anytime you get somewhere where you're like, wow, that's kind of complicated, maybe I don't want to stick this all in here and figure it out, but it's the smaller piece, which is just dealing with a single character instead of dealing with a whole string, let me write a function that'll actually do it, or a method that'll actually do it. So what I'm going to do is I'm going to append to my result what I get back by calling encrypt a single character, so I'll just call it encrypt car, and what I'm going to pass to it is the character that I want to encrypt, and I need to also pass to it the key so it knows how to do the appropriate shifting to encrypt that character. Okay? And after it does this encryption, I'm just going to say, hey, well, if you've successfully encrypted all of your strings, what I want to do is return my result. Right? That's your standard string idiom, right? I start off with an empty string. I do some kind of loop through every character of the string. I'm going to do the processing one character at a time and return my result. Right? Everything in that function that you see, or in that method that you see, except for that one line, should be something you can do in your sleep now. You've seen it like over and over. We just did it a couple times today. We did it a couple times last time. It's the standard kind of thing for going through a string one character at a time. And now we reduce the whole problem of encrypting a whole string to the problem of just encrypting a single letter. So what I'm going to have in here is private, and this is going to return a single character called, and this puppy is called encrypt car, and it's going to get passed in some character to encrypt as well as the key that it's going to use to encrypt it. Okay? And now I want to figure out how do I encrypt that single character. Okay? So what's something I could do to think about how this character actually gets encrypted? How do I want to do the appropriate shifting of the character? So let's say I've gotten an uppercase A. Let's assume for right now all my characters are uppercase. As a matter of fact, that's a perfectly fine assumption to make. The solution you've gotten to it assumes all the characters are uppercase. So assume all the plain text is uppercase, and I want to return to you the encrypted cipher text also in uppercase. let's say I've gotten an uppercase A, okay? And my key is 3. So I want to do is take that A somehow and convert it to a D, right? How do I do that? I want to add 3 to the character, okay? Now the only problem is I might go off the end of the character, right? I might, if I just add 3 and I have a Z, if I just had the A and go to D, that works perfectly fine. But if I have a Z, I'm going to get something like an exclamation point or something I don't know because I go off the end of the character. So I need to do slightly a little bit more math. And what I'm going to do is say take this character and subtract from it uppercase A. That's going to tell me which character in the alphabet it is, which number character it is, right? Now if I add the key, what I get is the number or the index of the shifted character, right? So if I had an uppercase A and I subtract off uppercase A, I'm going to get a 0. I now add the key, so I get 3. And you might say, well, if you just convert that to a character, you get a D. That's perfectly fine. Yeah, but if I had a Z and I subtract off an uppercase A, I get 25. If I add 3 to 25, I get 28, which is now outside the bounds of the alphabet. How do I wrap around that 28 back to the beginning of the alphabet? Mod it by 26, or we do what the remainder operator by 26, right? So what that does, it says if you've gone off the end, basically when you divide by 26 and take the remainder, if you've gone off the end, it kind of gets rid of the first 26 and wraps you back around the beginning, okay? So if I do that, this will actually work to get me the position of the character wrapped around. And once I've gotten the position of the character, here's the funky thing. I need to add the A back in, okay? Because if I had, let's say, an uppercase A to begin with, and I subtract off uppercase A, that gives me 0. I add the key, that gives me 3. I do the remainder by 26, or 3 divided by 26, its remainder is still 3. So now I have the number 3. I need to get that 3 converted to the letter D. How do I do that? I add the letter A to that 3. Okay? So any questions about that? Now the final funky thing that I need to do is if I want to assign this to a character, I can't do this directly. Notice if I try to do this directly, I get this little thingy here. And you might say, Meron, what's going on? Like you told me characters were the same as numbers, and everything I've done so far has to do with numbers. So why can't I just assign that to a character? And this little error message comes up. And this has to do with the same thing when we talked about converting from real values to integers. Remember when we went from a real value to an integer? We said you lose some information if you try to truncate a real value like a double to an integer. So you explicitly have to cast it from being a double to an integer. Same thing with characters and integers, right? The set of possible integers is huge. It's like billions and billions. The set of characters is much smaller than that. So if you want to go from an integer back to a character, you need to explicitly say, convert that integer back to a character. So we need to explicitly do a cast here back to a character. Okay? And if we do that, then we're happy and scrappy. All right? Did I get all my parens right? 1, 2, 3, 1, 2, 3. All right. Why is this still unhappy? Oh, duplicate variable CH. Yeah, let me call this C. All right. Actually, let me make my life easier. This is the thing I just want to return, so I'm just going to return it. I won't even assign it to any temporary variable. We'll just return it, because now I'm upset. No, I'm really not upset. We're just going to return it. Okay. So hopefully that will give us our little Caesar cipher. Okay, so let's go ahead and run this and see if in fact it's working. Any questions about this while this is running? I'll sort of scroll this down a little bit so you can see what's going on for that single character. All right, so this was my Caesar cipher. So we say et tu, Brute, illegal number format. Yeah, because that's not the thing I wanted to encrypt. My encryption key is 3. Then I will give it the plain text I wish to. Like everyone's like, what did he do? Yeah, sometimes it's the obvious that's wrong, and you just need to read. All right, there we actually go. Now there's a little problem here. See, the little problem is these spaces actually got encrypted. We don't want to encrypt spaces. We only want to encrypt things that are actually valid characters. So we're not quite done yet. What we need to do is come back over here and say, hey, you know what? For my encrypt character, I wasn't quite as bright as I thought I was. I need to make sure this thing's actually an uppercase character before I try to encrypt it. So we can sort of do that. If I'll just call my little friend character, and the thing we want to say is uppercase, or let me actually, okay, we'll just say is uppercase, and I'll pass it CH. So if it's an uppercase character, then I'll return this. Otherwise, what I'll do, I'll tab this in, is I will just return CH unchanged. Okay, so if I've gotten something that isn't actually a character, then I'll return yeah. Why is this unhappy again? Oh, semicolon, thank you. All right. Now I got an extra one. Notice it doesn't give me an error on the extra one because actually semicolon without a statement is the empty statement. It's perfectly fine. But thank you for catching the stray semicolon. So we'll go ahead and run this, and we'll try our friend et tu Brute again. Sometimes it's all about testing, and so we have et tu Brute, and now we're okay because we're not encrypting anything that is not a letter, right? So sometimes we think we're okay. We need to go back and just make sure we actually do the testing. Any questions about this? If this all made sense to you, nod your head. If this didn't make sense to you, shake your head. Feel no qualms about shaking your head. If you're somewhere in the middle, sit there and stare at me. No. If you're somewhere in the middle, shake your head. Okay. Why don't I need an else statement like say here? Because if I hit the return, I return from the function immediately. And I never actually get down to this return. So if I hit this return statement, I'm done with the method. As soon as I hit that return, it doesn't matter if there's any more lines in the method, I'm done. I actually return out. Okay? So the one other thing we might like to do with this that doesn't quite actually work right now, let's actually try running this and I'll show you what happens just to show you that it's bad times, is if I actually encrypt something like et tu Brute and I want to decrypt it, I might say, hey, try to use -3 as your key. And if I try to put in the text, I don't even remember what the text was that I wanted to encrypt. I get this funky thing with question marks, and it's just not working to move in the negative direction. So I want to allow for my Caesar cipher to also be able to decrypt information, which means if I got a Caesar cipher by encrypting with a key of 3, if I give it the text that's been encoded and I give it the key -3, it should shift it back 3 letters and actually work for me. So how do I do that? Well, it's something that has to deal with each individual character. If I want to encrypt each individual character, I need to figure out what's the right way of using the key. Okay? Think about a key of -3. What's a key of -3 equivalent to? A key of 23, right? A few people mumbled it, so we'll just throw out some candy, right? Because if I want to go 3 in the opposite direction, if I want to go 3 sort of this way as opposed to this way, it's the same thing as going 23 characters in the opposite direction. Okay? So if I want to think about doing that, I can say if my key is a negative number, so if my key is less than 0, there's some shifting I need to do of the key to actually get this puppy to work. Okay? So if my key is less than 0, as a matter of fact, I'm going to do this once down here. So rather than doing it and encrypting each character, I'm going to do it over here by saying, you know what, once I shift my key over, I'm going to use that same key to encrypt all my characters. So I want to do the shifting just once up here. It makes sense to do it once for the string, and then I'll use my updated version of key. So here's what I'm going to do. I'm going to say take the key, and the way I'm going to update key is I'm going to say it's 26, and this looks a little bit funky, but I'll explain it to you in just a second. Modded by 26. And you might say, Maron, why do you need all this math to actually pull it off, right? Because if you do something, you could say, why can't you just take 26 and subtract from it your key, right? So if you want to say minus or add to it your key, so if you want to have a key of -3, isn't that just the same as adding -3 to 26? You'll get 23, aren't you fine? Yeah, that's fine for sufficiently small values of key, right? So if this thing actually is -3, -3 gives me 3, and if I were to, missing a minus in here, sorry, my bad. I had 2 minuses, I want to have another minus right there. So if key is -3 and I take a negative of -3, that gives me 3. 26 minus 3 by itself would give me 23, which is the value I care about, and that's perfectly fine. Okay? But what happens if this key that someone gives me is something, for example, that's larger than 26? Right? That's kind of bad times. Because if I subtract a number that's larger than 26 from this 26, so if this happens to be let's say 27, and I say minus 27 is positive 27, and I subtract 27 from 26, I get -1. That's bad times. So the reason why I have this 26 in here is it says, first take the key. They gave you some negative value. Take the negative of that, which gives you some positive value. When you mod it by 26, you will guarantee that that value that they've given you is less than 26, right? Because if it was 26, that 26 mod 26 is 0. Something larger than 26 gives me a remainder. So as long as I mod by 26, I will always get back the appropriately mapped value less than 26, and then I will subtract that from 26. Okay? So just to make sure this actually works, what I'm going to do is in my main program. I'm going to say encrypt Caesar using this key. And then, so I have some ciphertext. I'm going to now, well, actually, let me write out the ciphertext, so I'll still do this println. And then I'm going to have some other string, new plain, and new plain is just going to be doing the encrypt Caesar, on my ciphertext, so that should be my encrypted text, with the negative of the key, right? So I want to essentially switch back to what I've gotten. And so I'll have println new plain, quote, plus whatever the new, man, I cannot type today to save my life, all right? Println, thank you. All right, so now I run this puppy. In our final moments together, 3, et tu, brute. Oh, well, at least I got back, even though I misspelled it. I got my mixed up characters, and then I got my new plain text, which is the same as my original text, which is I got just by essentially shifting in the negative direction. Okay, so any questions about that? Alrighty, then we're done with strings for the time being, and I'll see you on Wednesday.